All right, so welcome back, February 12th. Today, it doesn't really work. It's not worth 2 days of notes, but it is complicated enough that we'll get all the notes in today, and we'll take a full day to answer some questions. So today's the last new day of notes, and then it's review, test. So looking at the notes packet, growth and decay differential equations. Okay, we've done differential equations already. Differential equations is where you have dy dx equals whatever, x times y, where we separate and integrate. Separate, then integrate. So we have done differential equations. That's what we started this unit with long ago. We did differential equations, and then we jumped to slope field stuff, and now we're going back to differential equations, but a special type of differential equations. And the good news is, I guess this is good news, we've done some of these types already. We just didn't know that they were this type. So in some ways there's nothing new today, because at least in terms of methods and what we'll do, we've done it all before. It's just we're going to put a name on a special type of growth or differential equation. Again, we've done them before. We just didn't know that that's what they were. All right, we'll create and solve differential equations which describe the rate of growth or decay of a function in a situation. To do this, first thing we need to remember is proportionality. And so this goes way back to like Algebra 1, I think. The statement y is proportional to x translates to this equation. If y is proportional to x, do you know what equation that leads to or that means? Okay, so y equals x is sort of right. That's an equation where y is proportional to x. That's true. But that's not the only equation where y is proportional to x. So yes, if x doubles, y doubles. If x triples, y triples. But there's possibly a multiplier in there. So y equals kx. And k is the constant of proportionality. In fact, in 8th grade, or in algebra, they would say, y is proportional to x. If x is 3 and y is 6, find k. And so that was your first exposure to this would be, plug in x, plug in y, and figure out what k is. Obviously, we're going to move a little bit past that. How about m is proportional? You know what? Another way to say this is proportional means equals k times. That's one way to translate that. We're always figuring out how to translate, English into math. Is proportional means, or is proportional to, I guess, means equals k times. Is proportional to equals k times. So if we say m is proportional to the square root of w, that means m equals k times the square root of w. So that is proportional to sticks a k in there. And we'll still have to find k like you did long ago, but instead of giving you two little things, it's going to be a lot more complicated than that. The rate of p with respect to t, okay, we got to know how to translate that, is proportional to equals k times p. So something equals k times p, that's an easy one. But what is this rate of p with respect to t? How could I translate that into math language? What is that in terms of variables? Rate of P with respect to T. That's dP dt. And so this now is a differential equation because it's got a derivative in there, and we would separate and integrate. In fact, there's the next question. In the above equation, how can you solve for P? Well, separate and integrate. Get all the P stuff on one side, all the T stuff on the other side, and then integrate. And this happens in quite a few like real world, real life situations where the growth of the material is proportional to like how much of the material is there. It happens in nature. The growth of rabbits in a population depends on how many rabbits there are. And the more rabbits there are, the faster it grows, that kind of thing. Also in bacteria. The more bacteria, the faster it grows. And so this is, yes, it's math, but this is really some real world stuff. And I know you're like, well, what am I going to care about the population of rabbits or water evaporating? But yeah, some of you, you go into engineering, you need to know that kind of stuff. And this is where you would use it. All right, number one, water evaporates. And by the way, the first thing we're going to do on like all of these is not solve anything yet. It's just write the equation. So just working on translating English into math. Water evaporates from a puddle at a rate proportional to the square root of the amount of water present. Write a differential equation describing the rate of change. Okay, so a rate, that sounds like dW dt if W is the amount of water. After a few of these, you're probably going to stop writing what your variables mean because it's going to be kind of obvious. But for the first few, we'll make it really clear. So that's how the water rate is changing. Is proportional to, so that means K times the square roots of the amount of water. So the square root of what? So which variable goes under the square root for this one? W. And that's all number 1 through 5 anyway, wants us to do. We're not separating or integrating yet. We're just making sure we can write the equations. Number 2, the number of giraffes in a large preserve increases at a rate proportional to the 10th root of the population. Okay, so rate, that's d something dt, and I guess if we're talking about giraffes, we'll go dg dt. So rate is dg dt is proportional to k times 10th root of the population. So 10th root of what goes under the square root, or the 10th root on this one? G, because the 10th root of the population of giraffes. And we're not really there yet, but that means we would probably rewrite that as G to the 1/10. That would be easier to integrate in a moment. Why don't you try number 3 and number 4? Again, all you're doing is writing the equation. So write the equation and go ahead and still label the variables. I know you're going to get tired of that and probably not do that every time. But for now, write the equation for 3 and 4 and label the variables. D what? dB for bacteria. That works. You could have put C for cells or maybe even N for number, I guess, but I'd probably go bacteria. But C for cells would work as well, either one. So yeah, dB dt is the rate of the bacteria cells. Monty, what goes on the right-hand side? K times what? What is it proportional to? So K times T. So this one is different. This one's different because usually, like our main variable is over here, is usually what has been happening. dW dt with a W, dG dt with a G, dA dt with an A. This one was different. It's not proportional to how much bacteria is there. It's proportional to the time. Again, it depends on the physics and the biology and the chemistry of what's going on. We don't have to understand that. We do just need to make sure we can, understand and translate from English to math. Try that last one. Try number 5. So yeah, F is frogs, dF dt. Ava, what's the rest of that equation? Cube root of the population. So yes, the cube root of F. Yeah. Okay. Now we've solved differential equations that look like all of these. So the only thing, I don't want to minimize it, but the only thing we're adding to our knowledge today is like setting up these equations based on words. So that's usually not too bad. The only one that sometimes tricks us is if they put the t variable over there instead of the main variable of the problem. But just read the problem carefully, and usually the setup isn't the problem. I mean, that's the new part. That's usually not the main issue to deal with. All right, so now we're going to get into actually solving them, not just setting them up. Number 6, a population of frogs increases at a rate proportional to the cube root of the population. Wait, that's exactly what was in number 5. All right, so that's the same setup as number 5. I'm going to start up here in the corner because I know it's going to take some room to solve this thing. So dF dt proportional to cube root of how many frogs there are. Okay, if the population changes from 27 frogs to 216 frogs in 1 year, what is the population of the frogs at the end of 5 years? Okay, because of the constant of proportionality and because the constant of integration, like whenever we get around to integrating this, a c is going to show up. We're going to have 2 constants that we have to solve for in almost all of these problems. Because we're going to have enough information to figure out what k is, and then when we integrate, we're going to get a c, and we'll have to have enough information to get that. So they're always going to be giving us a lot of information because we're going to need to use it to find k and c. People write this information in a lot of different ways. I like to write it as like a table of values, almost an ordered pair. That way I can keep up with everything. This one's worded a little bit weird. So it changes from 27 to 216. So 27 to 216 in 1 year. So I think that means after 1 year, there were 216 frogs. At the start of this experiment, there were 27 frogs. So that gave me 2 pieces of information in one statement there. So we started at 0.27. We didn't end with, but after 1 year there's 216, and then we may as well put this on the table as well. What is the population of the frogs at the end of 5 years? Okay, so the whole point of this question is to fill in this orange box here. What is the population after 5 years? we still have a long road ahead of us here. We need to separate and integrate, and then we'll worry about using those information. So cube root of f, I don't like cube roots because it's not the cube root part. I don't like roots because I can't really integrate them. I'd rather powers. So I'm going to change that to f to the 1/3. Some people will change it later, but you got to change it eventually because you can't integrate a cube root. Let's move the f over. This is the separate step. So df over f to the 1/3 equals k dt. Again, that almost always gets you a third or a fourth of the points. That gets you a point on the AP test. You're like, wow, all he did was like one little algebra step. It's that important that they want to see it, and they'll give you a point for it. Now we're sort of ready to integrate. I don't really like f to the 1/3 in the bottom, so I'm going to write that as f to the negative 1/3. That way when I integrate, things are a little easier. Okay, speaking of integration, so Lauren, on the left-hand side, what's the antiderivative of f to the negative 1/3? F to the, you were right, f to the 2/3 and then 3/2. Yes. You amazed you got it right?
It's been a break.
It's been a break.
I'm not going to lie to you. I think I forgot a lot of things.
Well, you didn't forget that. Increase the power by 1, divide by the new power. There's sort of a plus c there, but remember we're going to let the plus c usually go on the other side. That's a hint for Anders when he integrates the right-hand side here. What's the antiderivative of k dt?
Is k a constant, right?
Yes, good.
All right, so you just do.
Is that too excited about that, or? Because it's not k squared over 2.
Yeah. You just do. Is it just kf?
But I'm doing with respect to t,
Just kt.
so kt. But you're right. There's like 3 things people put. K squared over 2. That would be if this was dk. But you were right that that's a constant. The other thing is to kind of get them confused and say that it's kf. But no, it's dt, so you're right, it's kt, and then plus c. Okay, now we kind of have options here. So I've got to figure out what k is. I've got to figure out what c is. And that makes sense because I have 2 pieces of information, and probably that will help me figure those things out. I do need to solve for f at some point though, so I think I want to solve for f first. You don't have to solve for f first. Like you can start plugging things in and figuring out k and c. So it's kind of up to you, and it kind of depends on the problem. But I'm going to multiply through by 2/3. That'll fix the 3 halves. Oh, this is that trick. If I have not identified k and I have not identified c, what's 2/3 times k times t? This is like the fuzzy math thing. You're like, wait a minute, is that really? What's if I don't know what k is yet? If k can be anything, what's 2/3 times k? Still k. And 2/3 times c? Still c. So be careful, those are different k's and different c's now. Again, some people that really bugs them, so they'll put a subscript on there to kind of be like, hey, those are not the same k and c, but it doesn't really matter because I haven't started figuring out what they are yet. All right, I'm debating here. Both of these are perfect cubes, 3 cubed and that's 6 cubed. So they're going to fit in nicely when I put them in right here. So again, I could put both sides to the 3 halves, or I can I can start using these right now. It's probably easier to use the information now, but what we've done every step before this, or every problem before this, is to solve for f first. It doesn't matter, so I'm just kind of debating in my head, like for consistency's sake, I should solve for f first. But for ease of problem's sake, I should plug in my values first. It doesn't matter. Do you have a preference? You want to solve for f, or you want to plug things in? I tried to lay out the case for both. I like plugging them in. I'll solve for f later, and that's not really hard. So let's plug them in. I'm probably going to need both to figure out k and c. Which do you think would be the easier thing to plug in first? Which is usually an easier value to deal with? The 0. So it doesn't matter, but life's going to be easier if we use the 0 first. So 27 goes in for f. 0 goes in for t, and yeah, that's really nice. That wipes that out. So 27 to the 2/3. Let's see, the cube root of 27 is 3. 3 squared is 9. So c equals 9. Okay, so I'm going to rewrite my equation, but now I know what c is. And now let's use the other piece of information. So 216 in for f. One in for t. Let's see, cube root of 216. Well, this is where it helps if you recognize some of your perfect squares and perfect cubes. You may not recognize that 216 is 6 cubed. So the cube root of 216 is 6, squared is 36. So k is 27. So I'm going to rewrite my equation, but now I know what k is. 27t plus 9. And then now I'm going to solve for f. So I'll raise all of that stuff on the other side to the 3 halves. So that's sort of my solved equation. Sometimes that's all it asks for, but this problem wanted to know f when t is 5. So, there's one more step to do. I just need to plug in 5 for t. And hope this works out. Although there may be a safe stop in our near future here. 27 times 5 plus 9 to the 3 halves. Safe stop, for sure. Because I don't want to go any further. It does work out, like they rig these a lot of times to 27 times 5, that would be 135. Plus 9 is, actually, hold on, let me box this in because that's where I'm stopping. Plus 9 is 144. Like, oh, that's a perfect square. The cube root of, or the square root of 144 is 12. I still would have to know what 12 cubed is, so either way, I may as well have safe stopped it way back here and not mess with this thing. A lot of times this would be a calculator part of the test because sometimes you're going to get weird, ugly answers, and they want you to get them, and so you'd have a calculator. Okay, so what is new about this problem that we haven't done before? The new is the constant of proportionality, which introduces an extra constant to solve for. which is why they gave us two pieces of information. So in some ways the calculus is the same. Write the equation, separate and integrate. That's the calculus. Then we're done with calculus. After that it's algebra, algebra, algebra. Please be careful. Number 7. A bacteria starts, so already I'm thinking I've got a piece of information there. If it starts with 500, what time is that? 0. So some code words here, similar to physics. Like initial population, starts with, those kind of words. Grows at a rate proportional to its size. So that means dB dt is proportional to equals k times what? So k times its size. So what is size referring to? Is it going to be, what's the rest of this equation? B. It's proportional to how many bacteria there are. After 3 hours, okay, so now we're back to my information table here. After 3 hours, there are 8,000 bacteria. Part A, find an expression for the number of bacteria after T hours. Okay, so that's find the equation that we can use to solve any of these problems. So we need to separate and integrate. So dB over B equals K dt. There's my separate. Next I need to integrate. I can have some helpers on my integration side of things. Joe, how about the antiderivative of dB over B? Good. That's kind of the tricky one because people frequently want to write that as b to the negative 1 dB, which isn't wrong. And then they try to use the power rule, and then that wouldn't work. Now, if you do this and try the power rule, you get b to the 0 over 0, and hopefully you realize, wait a minute, that can't be dividing by 0, so yeah, this is the special case where it's natural log of b. Mia, how about the other side, the antiderivative of k dt? Good, kt plus c. Alright, I got two variables I got to deal with there. Yeah, I don't want to solve for, I don't want to plug things in yet. I want to solve for b. So what could I do to solve for b? Algebra All-Stars. This is we did this 2 weeks ago now. What's that? The E thing, yeah. Either E both sides or fish hook it, however you want to phrase it. So E to the kt plus c equals b. But then we did some fancy footwork up here with this kt plus c. Do you remember what we could do with that? That c can be a constant out front. It's a different c, right? Because it's the same thing as e to the kt times e to the c. Okay, so I'm done with the calculus. I'm not done yet because I need to use these pieces of information to figure out what c and k are. So, again, the zero's almost always the easiest one to use first. I can't think of a time when it's not, and I just don't want to say always, because I don't know. So let's plug in the 0 one. So 500 in for B, C, E to the K, times 0. Oh, we like k times 0 because that's 0. We like e to the 0 because what's e to the 0? 1. So what's c equal to? 500. So that was an easy start. So now we know c is 500. So b equals 500 e to the kt. Don't know k yet, but I do have another piece of information to use. So 8,000 equals 500 e to the k times 3. Okay, well this one's going to be a little bit more of a pain to figure out what k is. Let's divide by 500 first. Let's see, 80 divided by 5 is 16. What would you do next to start to figure out what k is? How do I get that 3k out of the exponent? Algebra All-Stars who've had a week off. So let's natural log both sides. That way that 3k can come down front. And another bonus is natural log of e is 1. So k is natural log of 16 over 3. Alright, I don't have a calculator. I don't want to mess with that right now. So I'm just going to leave it like that. And that's fine. Like, that's an exact answer. It's a safe stop. I don't know what number that is, but if I need it, then I can get a calculator and go from there. So I'm going to leave it like that. And I am going to need it, so I will grab a calculator, but I don't really care what it is, like what the value is. But I'm going to do the thing where I store it as k. That way I'll have it. So whenever I need it, like I see there's a few more parts to this problem, then it's already in my calculator and I don't have to keep typing in natural log 16 divided by 3. Okay, how many bacteria are at the 4-hour mark? So back to my table here, if I plug in 4, so where'd my equation go? 500 e to the k times 4. But I know what k is now. K is not an unknown. K is a constant, and I know what it is. So now this is just a plug it into the calculator thing. 500 e to the 4k. And again, unless it specifies, it will always want you to round to 3. That seems a little weird when you're talking about bacteria because you can't have 0.7 bacteria. So I feel like that one probably would have asked us to round to the nearest bacteria. Lastly, when will the bacteria reach 30,000? So that's the opposite problem. That's the bacteria is 30,000. What time will that happen at? So again, this is another algebra problem. Let's divide by 500. So 60 equals e to the kt. And again, I keep writing that, but I know what k is, so don't get confused. I know what k is. It's in my calculator. It's some weird decimal. So that's not an unknown. I know what k is. What do I do to get or what should I do next? Rabia, what should I do next?
You have to
Well, I don't know that you can put it in the calculator yet. I would natural log both sides to get that KT out of the exponents. Natural log of E is 1. So T then is natural log of 60 divided by K. And really, that would be a safe stop because you've defined what K is. So you could box that up, but probably want a real answer here. Natural log of 60 divided by K, 4.430 hours. Okay, we'll stop there. And we'll say that for our worksheet, let's see, there's a worksheet number 3. There's a bunch of problems, 1 through 14. Some of those get easy. I think we didn't do a decay problem. So let's say we're going to do worksheet 3. 1, 2. We could skip 3 for now. 4, 5, 6. Yeah, you could. Let's just say 1 through 10. It kind of doesn't matter because tomorrow all we're going to do is assign the rest of them. So, split it up however you want. By the end of tomorrow, we'll need to have seen them all or tried them all. At least that'll be tomorrow's assignment. So tomorrow I'll just work some from 1 through 10, and there won't be anything new in terms of. Actually, we'll need to do the last 2 examples, and then we'll work some from 1 through 10. So, didn't get to all the examples, but that's fine because we got 2 days to do it.